So in this, I know that this is like the entry into all this stuff, but typically as we move forward, we orient our axis so that the magnetic field vector, right? Is that what am I saying that correctly?
Mm-hmm.
Magnetic field vector and the velocity vector are coplanar, so that even if we're looking at three-dimensional spaces, one is going off here and one is going off here, we'll orient our axis so that they're coplanar, so that we can use the right-hand rule in that way and not have to do a bunch of trig.
Yeah, and we won't ever get a problem that yucky. And in fact, if we do, we're just going to use, we'll probably be given all the components like this, and we won't even bother drawing a picture because it would be so ugly. We'll just use this equation to figure out the magnitude. And I don't think it ever asks you for the direction if you have to use all of this because it's complicated. Well, you kind of get a sense for the direction. Well, no, actually, now I'm thinking about it. Your resultant answer would be in terms of I hat and J hat and K hat, which is in, yeah. So whenever we do use a pictorial diagram and use our right-hand rule, it's going to be usually a very, in the X, Y, and Z direction, not off in some random direction, typically. So I put a whole bunch of concept questions in the lecture so we can get practice using our right-hand rule. That way we can practice all these again next week, but it's better to practice now and reinforce it while we just learned it. Okay, so the first question, if you have a beam of electrons which have negative charge coming straight towards you, so this is the beam of electrons coming straight towards you, and you point the north pole of a magnet directly above the beam, so the B field is pointing down, which way will the electron beam be deflected? I know, no, I know. This is, did I tell you guys this is called the physics gang sign? Oh my gosh, I forgot to tell you this is the physics gang sign. So when we're walking down the hallway and I say, hey, what's up, Chris? That's how we know you've taken physics 222. Because math is just not as cool as physics. All right, you guys ready to vote? All right, who thinks the answer is A, up? B, down? C, to the left? 1, 2, 3, 4, 5. D, to the right? 1, 2.
I want to go for left.
Left, okay. 6.
I go for left.
7, okay, 7 for the left. How many people for the right? 1? Oh, Wes, everybody defected. Okay, do you want to go to the right?
Oh, there are electrons. No, left.
I'll go for left.
Left? Okay. Oh, Wes defected. We just didn't even have to discuss this.
We talked about protons.
All right, see, that's great. First one, and you guys are getting the trick. So they said electrons, so your right-hand rule would look like this, but it's electrons, so it's going in the opposite direction. Yeah.
Wait, so wouldn't electrons be the electrons?
No! Never use those words in my classroom. No, no, no. They're banned. No, no.
Why?
Because I don't ever want anyone to be confused. We only talk about the right-hand rule in here. Okay? You might talk about something else with an L in the front, but not in this classroom.
Can we discuss this?
What's that?
Can we discuss this in the hallway? So it's not in the front?
No, do not corrupt any of my students.
No, without students around.
With other people. Don't talk to me about it. I don't want to hear it. All right? This is the right hand rule. If it's electrons, it's the opposite of what your right hand tells you to do. I swear people have gotten mixed up. So I have a ban on that three-letter word, or that three-word combination in my classroom. All right, I think we've all been warned.
Well, I didn't hear what it was all about. What was it?
Nothing.
Don't worry about it.
Yes, don't worry about it.
No, you really don't. It was a theory.
No, it's fine theory, but don't spread it around because some people aren't there yet.
In my head,
Okay, good. But don't use that word ever.
if I don't use the word, are we good?
We're good. We're good. Okay. Okay. When a charged particle moves through a magnetic field, the direction of the magnetic force on the particle at a certain point is what?
What was the answer to the last one? C.
What everyone else voted for.
Well, what was the direction?
It was
Left.
left.
Left. Okay.
You're left. All right, who's ready to vote? Okay, you're whispering. Who thinks the answer is A? B? C? Okay, that's everybody. You guys all got C?
Yeah.
Yeah.
Wouldn't it be E though? Would it depend
Yeah, that's what I
on
was
the
gonna
charge?
Particular regardless of the structure.
Oh, that's
Yeah.
That's the rule.
There we go. Okay, a particle with charge Q equals -1 coulombs is moving in the positive Z direction at 5 meters per second. The magnetic field at that position is given by that vector component term of B. What is the magnetic force on the particle? And we actually haven't done anything like this, so I almost feel like I want to do this one on the board.
Thank you.
All right. They tell us that the charge Q is a negative charge, first off, negative, and it's moving in the positive Z direction at 5 meters per second. So the velocity is plus 5 meters per second, and what's the unit vector for the Z direction? Yeah, K hat. The magnetic field, they give us as 3I hat minus 4J hat times T. So another way to write this velocity vector would be the x component is 0, that's v sub x. The y component is 0, that's v sub y. And the z component is plus 5. Another way to write the B field, the Bx component is 3, the By component is -4, and the Bz component is 0. So this is our big long definition using A, B, and C. So it might be actually helpful to rewrite this in terms of our forces and stuff. So F of B would be Q times the cross product here. So I hat A is V, little b is big B. Okay, so we've got Vy, Bz, Bz, By minus J hat, Vx, Bz minus Vz, Bx plus K hat, Vx, By minus Vy, Bx. All right, so that's what we're going to use. So the force is Q Now look at the I hat equations. It takes Vy and Bz. Vy is 0, Vz is 5, and Bz, which is 0, and By, which is -4. So Vy was 0, Bz is 0, minus Vz, which is 5, times By, which is -4, okay, the j hat direction, we've got Vx, which is 0, times Bz, which is 0, minus Vz, which is 5, and Bx, which is 3. And Vx and Vy are both 0, so this is going to be 0 minus 0. Okay, to get rid of all the zeros now, we've got I hat times -5 times -4, so that's 20. Minus j hat 0 minus 5 times 3 is -15. And then the k hat term is 0. So we don't need to write it. Oh, Q is nice. It's -1c. -1 coulombs. We can distribute that through. So we've got 20 meters per second times I hat. And then this negative I'm going to put inside here, so this becomes plus 15 meters times Tesla per second. J hat. Distribute that negative through it all, and I get -20 newtons in the I hat direction minus 15 newtons in the j hat direction. Okay, so that's a complete answer, because when you put it in vector component form, it includes all the angle information. So you don't need to go an extra step and find the direction. Let's see what they wanted to know. What is the magnetic force on the particle? Okay, we figured out? D, okay. This would not be a test question, because if you make an algebra mistake in here, you're not getting partial credit, and that sucks. So this doesn't test your conceptual understanding, it tests your math skills. And if you make a math mistake and get it wrong, that's not a good measure of your physics knowledge. So you should actually be happy, right? Because that would be a lot for a multiple choice question. It could, yeah, I mean, it could make a good test question, just not a good multiple choice question. Yeah. And that's actually a good choice for for a bonus. Yeah, yeah. Okay, any questions about this? You guys actually seem pretty happy with it. This is like total yuck to me.
No, we can handle that.
You can handle it, all right.
I think it's easier if you draw the x, this thing you draw earlier.
Oh, the matrix?
Yeah, and it's much easier. Like,
right.
You have to worry about that, and after all, it's just multiple by -1. That's it. Change the size.
Oh, and just write the matrix when you're done?
Yeah.
Works too.
Plug a matrix into a calculator.
That's true. Mm-hmm. What would you tell your calculator to do with this matrix?
You got to store it as the exponent 0, 0, plus 5, and hit store to a letter.
Oh, I mean, I know how to make the matrix, but if you wanted to get the result of that out, what would you tell your calculator to do to that matrix? That's the part I'm not sure about.
It would be the RREF.
I don't think it's not RREF, because yeah, that's something else. That's reduced row echelon form. I'm pretty sure that's not the same thing, but I could be wrong. It's been a long time since I took linear algebra.
The same cross product?
What's that?
This isn't cross product?
This is cross product, but you can have your calculators do it for you.
Yeah, you can just
You put in the
type
two
calculate your
vectors.
cross product, right?
On the matrix, you say cross product and you give it the matrix?
Yeah,
Oh,
that's what I do.
okay.
I just tell it cross and then the matrix.
Oh, okay. I didn't know that was, let me see. I have an older calculator, but it has a lot of matrix functions I've never used. So let's see. Second matrix math. I can find the determinant, the norm, the eigenvalues, and the eigenvectors.
Hit catalog, hits the letter C.
I don't actually think I have that.
Scroll down until you see cross. Then it's cross. Yeah, there it is. Cross P. That's it. Just put cross. Yeah, you just put your matrix in.
I have a lot of things, but I don't have that. I guess that's a good reason to upgrade.
Because it involves brackets.
Well, I guess you guys can show each other at lunch. Maybe I can figure out if my calculator actually does it, but I don't think it does. Sad. Okay, the next one, 27.5. A positively charged particle moves in the positive z direction. The magnetic force on the particle is in the positive y direction. What can you conclude about the x component of the magnetic field at the particle's position? Is everyone ready to vote? I'm not seeing anybody do this. Some nods, yeah? Anybody not ready? Oh, just one person. Okay, well, we'll go on. Who thinks the answer is A? 1, 2, 3, 4, 5, 6, 7, 8. Who thinks the answer is B? C? D? Okay, so how did you guys come up with A? Right-hand rule?
I mean, I always think of the z as going this way. So I just pointed towards the z direction.
Okay.
My thumb was the force in the y direction, and then wherever this would need to end up, which was the positive x direction, the way I did my axis.
The way you do your axis, yeah.
X, y, z.
Uh-huh.
Well, for you it would be x, y, z.
Yeah. Yeah. I end up doing my axes wrong half the time, so I always have to reference the way the book does it, or else I make mistakes. So I always do y up and z coming out. But if you get it, if you've got it in your head the right way, then it'll work. Yeah. So the way I did it using the book's method was I had positive z is coming out of the board, the magnetic force is in the positive y direction, that's my thumb, and then that would make my middle finger pointing to the right, which is the positive x.
Okay.
So that's the way I did it. Did anyone else do it differently, a different way?
Did it X, Y, Z? The regular Y, the Z?
The z going up like we do in math?
Yeah.
Yeah. I don't know why in physics we switch our axes around.
Yeah.
It's confusing. It's confusing, and I've been doing this for years. So let's make sure the book agrees. The book says it's C. Why? They could very well be wrong, but let me just double check. Here's my lecture notes. Oh no, we had this on problem, this one. Yep, Y, X, and Z. So I think that Z, positive moving, that's V direction. The force is positive y. I'm using my right hand. I think they're wrong. I'm just going to change the answer. I don't really see how they could be. I don't. It's like not that hard. So, yeah. Okay. Was this a different one? Oh. Okay. So this is the same question, but now they're saying, what can you conclude about the y component of the magnetic field? If everything else is the same, what would the y component be? All right, who thinks the answer is A? 2, 3? Who thinks the answer is B? 1? Scratching? 2? Okay. Who thinks the answer is C? Who thinks the answer is D?
I have no ideas.
Well, the only reason that I think this could be ambiguous is if those directions, it's not exactly along the x direction or the y direction or the z direction, and it's just generally going in that direction, but it has some other components, then I might say D. But if we assume that these are going strictly in the x, y, and z direction, then there should be an exact answer. And so, my fingers were still the way they were for the last problem, and my middle finger is still pointing in the positive x direction. So I would say it would be B because there's no y component of the magnetic field. Is that your logic too, Thomas?
Yeah.
But other people disagreed. So why did you guys choose A?
Right hand rule.
Yeah, I guess I was thinking like if this vector is going to be moving and then it would have a negative y component, then the thumb would have to move with it. So
Where'd the negative come? There's no negative y component.
No, I'm just saying if it's less than, if the y component of that vector, my middle finger the way I have it arranged, were to be in the were to move in the negative direction, were to have a negative component less than 0, and that would make my thumb have to move. So it wouldn't work. So, I mean, I guess it would be either 0 or greater than 0.
Oh, so if you're talking about at an instant after it starts moving, like if it starts rotating?
Right.
Well, that would introduce a whole nother wrench into the equation.
Like, if there's a component that's gonna push this vector here that way, which would be a negative y direction, then my thumb would have to move with it in order to keep that rule working.
Okay. Well, I think we have to take a snapshot in time. I mean, otherwise, if we don't take a snapshot in time, then at the moment it moves, it's going to have all its vectors in a new direction, which would be really complicated. So
I guess I was talking about movement, just the component. Like if part of that component is going in that direction, then it would have to shift it a little bit, I guess.
that's true, right? Yeah. Well, if it's not exactly along an axis, then it could have other components. Yes. Yeah. Do you have a thought?
I have a question.
Yeah.
So the particle, when it enters the force, or does it always have the force on it, and that's how?
As long as it's moving in a magnetic field, it will always have that force on it.
Okay. And so the magnetic field is created when the particle moves?
No. The magnetic field is just there. So imagine a permanent magnet is just like here, and the charged particle enters the B field. So think of like a particle accelerator where they're able to create a beam of protons, and then they've got a permanent magnet to create a magnetic field, and then they send that beam of protons and it's going straight, but as soon as it enters the B field, it suddenly gets that force on it. Let's see, B field is down. The force would cause those particles to then rotate as soon as they entered the field, but it would have the same force on it as long as the B field was the same.
So then the magnetic field at the particle's position would be the same as the force, and so it would have to be greater than 1.
Well, it's perpendicular, right? Because the B field direction's down and the force is perpendicular. So the way I'm understanding my right-hand rule, right? The direction is in the positive Z. The B field is in the, oh, the B field is in the positive Y. Was that different from the last problem? Oh, maybe I had it wrong from the last problem. I did. Oh, okay. My hand was wrong. So going back a problem to 27.5, oh, that's right. No, it's my thumb. So the velocity is straight out of the board. The magnetic force is my thumb. That's straight up. Okay, I did have it right. The x is in the positive. The magnetic field is in the positive x. And then nothing changes about the direction or the force in 27.6. And so my finger is still all in the x direction. So I conclude it's B. There's no y component for my finger. If we assume that the velocity is all in the z direction and the force is all in the y direction, then that has to be all in the x direction, the B field. But let's see what the book says. Yeah, so they say B, and I think this this is one that could use a little bit more clarity, so that we're sure that it's all in the x direction, or all in the z direction, and all in the y direction. So that's just the definition of the cross product. If A and B are in the y and z, or sorry, A and C are in the y and z direction, then B has to be in the x direction because they're all going to be mutually perpendicular if they're all 90 degrees apart. So. Any other questions about this one before we move on? About the last one?
Are we crossing V cross B or B cross V?
We're doing V cross B. Yeah.
And the book gave us the 20, is that what the answer was?
For that one? D, yeah. All right. Anything else? Let's ready to go on to the next one. All right, this is beating a dead horse, I swear. So this is the same problem. Now they're asking about the z component to the magnetic field. And so using the logic of the last problem, the z component better be 0 as well. Oh, they say not enough information given to decide. In that case, then they're saying that it might not all be in the x, y, and z direction. So let's just chalk these ones up to being very confusing because there's not enough information in the problem to really fully discuss them. So, right. All right. Where are we at for time? We do need to take lunch a little early today because I'm missing the staff meeting, and there's a discussion happening at 11:50 that Mateo wanted me to be in. So we've got 15 minutes left, so just let me know when we get to 11:45, because that's where we're going to have to cut it for lunchtime. Sound good? Okay, so we've talked about how it's going to cause a particle to rotate if it enters a B field with some velocity. And I talked about how this is just like uniform circular motion from 221. So to remind us of what those equations are, if you've got a particle that's rotating at a constant velocity, then it's the force is pointing towards the center of the circle. The associated acceleration we learned was called centripetal acceleration in 221. And the way the book writes that variable is a rad, rad for the radial component, because that acceleration is along the radius. And a rad was defined as v squared over r. So the force, this is still the magnetic force, so it's still defined as QVB cross, or QVB sine theta. it's also equal to mv squared over r. So that's a way you can solve for more information, such as the radius of the circle of those rotating particles. So if you have, let's say V is exactly perpendicular to B, as in theta equals, or phi equals 90 degrees, then F of B would be Q VB sine 90.